Hi and welcome. My name is Zhibing Guo. I'm an engineer in the Application Research Lab of Betasize, and I have been focusing on the research of application experiments. It's my pleasure to give a talk, and my topic is application of laser particle size system in cement industry. This talk will be divided into the following 5 parts. As we know, producing the cement to make the concrete is a costly business. Accurate and repeatable measurement of the cement particle size is an absolute necessity to reduce cost and provide an optimized distribution. This talk will focus on the size analysis of cement particles. First of all, I want to ask a simple yet complicated question. What is the size of a particle? This is a problem always bothers us because the types and shapes of particles in this world are too diverse. For example, for polystyrene latexes, they are very standard spheres, so their particle size can be presented by only one number, which is diameter. But for non-spherical diamond particles and for acicular tobacco fibers, how to find the diameter that can present their actual sizes? This question is not easy to answer. Let's focus on today's topic, cement particles. The most construction and building material is concrete, and its key ingredient is cement, which is the binding agent that creates the formation of concrete. These are electron microscope images of cement particles. We can clearly see the sizes of cement particles are not consistent. In other words, their particle size has a distribution. Apart from the difference in size, cement particles are different in shape and very irregular. So, if we want to measure the size of cement particles, which method should we choose? This is an irregular cement particle. The measurement method is to equate it into a sphere with the same physical properties, such as sedimentation rate, surface area, and volume. The diameter of the equivalent sphere is used to present that of this irregular particle. Different measurement methods will give equivalent diameters from different dimensions, which is the reason for the data variation caused by the various methods. Let's take a look at the different particle measurement methods. The measurement range is from 0.1 nanometers to 1000 microns. For example, the well-known sieve analysis is suitable for measuring micron-sized particles, and dynamic light scattering is for measuring nano and submicron particles. Well, for laser diffraction, it is appropriate for micron-sized particles with a wide range, covering from tens of nanometers to several microns. Many historical techniques have been used to measure the particle size fineness of the cement. The first were 45 micron sieves, which only provide the second largest dimension, and plein air permeability, which predict the compressive strength by a single number, and Vogner turbimeter. These techniques took a minimum of 5 minutes of measurement time, and they were limited to only providing a single number. Laser diffraction, however, became the instrument of choice in the 1970s. Why? Because this technique is easy and reproducible and is much faster than older methods. In addition, it calculates many more relevant parameters with which to optimize the cement particle size distribution. Compared with other measurement methods, what are advantages of laser diffraction? In this picture, static light scattering or laser scattering has a wide range, covering most of the particle size distribution of powder particles. Theoretically, it can measure particles from 10 nanometers to several microns. The single measurement time of laser diffraction is very short. Every measurement of the microscope, sedimentation, and sieving method that you may be familiar with takes at least several minutes. But if you use laser diffraction, you can get a test result in a few seconds. In terms of measurement speed and convenience, laser diffraction has great advantages. And with correct operation, The measurement results of a laser analyzer will have excellent repeatability and reproducibility. In other words, there is a small relative standard deviation between each test result. The D10, D50, and D90 of the laser diffraction refer to the particle diameter when the cumulative distribution accounts for 10%, 50%, and 90% of the total content, respectively. Here, the repeatability of D50 is only 0.17%, which is actually far less than the ISO standard for laser diffraction. After a quick introduction to the laser diffraction method, I want to talk about the significance of particle size control in the cement industry. The size of cement particle directly affects the hydration, setting, and hardening process of cement, as well as the strength and heat of hydration. There are several key particle size values in the size distribution of cement, which are 1, 3, 32, 65, and 80 microns. Only 1 to 65 microns are the effective component of cement. Particles less than 1 micron will be completely hydrated during mixing with water, and they will not increase the cement strength. When the content of 1 to 3 micron particles is high, the 3-day strength of cement will increase, but the content should also be appropriately reduced. Generally, the percentage of 1 to 3 micron, less than 10%, is recommended, and 3 to 32 micron particles. They play a leading role in the increase of cement strength, and it is reasonable to control the total amount to 65% to 75%. Besides, 32 to 65 microns have a low degree of hydration and thus are not wanted. Last, particles larger than 65 microns have no strength contribution, which should be reduced as much as possible. The hydration depth after 28 days of pouring is about 5 microns. This means particles larger than twice the hydration depth, which is about 11 microns, will always have a part of core that is not hydrated. The unhydrated inner core only acts as a skeleton in the concrete and does not contribute to the strength. As we see, the hydration rates of 16, 32, and 65 micron particles are 97%, 72%, and 43% respectively. Therefore, it is generally believed that 3 to 32 micron particles play a major role in 28-day strength, and particles larger than 32 micron, especially those larger than 65 micron, would have a low hydration rate and is a waste of clinker and should be reduced as much as possible. The laser diffraction method for measuring particle size was first invented commercially in 1974, and the first industrials to use this technique were coal, ceramics, chocolate, and cement. The particle size distribution or fineness of cement has been measured by laser diffraction in laboratories since 1975, so the cement industry was a very early adopter. With the laser diffraction analyzer, we are able to measure the fineness of cement in its natural dry state or as a wet dispersion, using industrial alcohol such as propanol or ethanol. As can be seen, both wet and dry dispersion methods yield the almost same result. Here is the wet analysis process when I measure cement particles. As you see, cement is well dispersed in a small amount of ethanol, and the results can be provided in less than 10 seconds. However, due to lower running costs, better statistical representation, and easier usage, the dry method is preferred rather than wet analysis in cement industry. Let's have a look at the dry analysis process. The cement is added into the funnel, and the vibrator feeder moves the sample into the venturi, and it is transported by compressed air through to the measuring cell. All we have to do in dry analysis is to add the cement into the funnel and wait. Then, 3 measurements will be done in less than 30 seconds. There's no need to use solvent. When making a wet analysis of cement, up to 5 different parameters need to be taken account, including solvent use, pump speed, need of ultrasound, ultrasonic dispersion time, and strength of ultrasound. When using the dry analysis, however, there's only one requirement, and that is the air pressure used, which is to make a pressure titration curve. You may wonder how particles are dispersed by only using the air in the dry analysis. Actually, dispersion is carried out by the following three reactions, which is shearing. It means strong centrifugal and shear forces applied to the particles due to airstream. Then particle-particle collision, as agglomerates with high kinetic energy collide with each other. Last, particle wall collision. This is the most effective dispersing effect, but it is possible to break primary particles if the air pressure is too high. Therefore, we have to avoid too strong or too weak compressed air in the measurement. To find the appropriate air pressure is very important. This involves measuring the cement at 4 different pressures, typically from 1 to 4 bar. For many applications in other industries, results can change at different pressures, but as we can see in this figure, the variation between results at 4 different pressures is minimal. Typically, a pressure of 3 bar is recommended for dispersion in conjunction with a vacuum to suck away the dispersed particles after they have exited the measuring cell. In addition to measurement of cement, it is possible to also measure additives such as fly ash, slag powder, and hydrated lime. Comparison measurements of the fly ash and different grades of cement can be made. As fly ash can be a good additive to cement, we can see the effect on the overall particle size distribution of each grade when adding 15, 30, and 50% addition of fly ash to these different cement types. From a research perspective, you can measure alternative additives and check the effect on the overall size distribution and determine how much to add to reach the optimal strength. Well, after talking about the laboratory analyzer, next I would like to introduce the online laser system, which is very important in the cement industry. We know laboratory-based laser systems improve the quality of the cement, but how can they be adapted online to produce the most optimized cement fineness? The particle size is determined by a ruggedized version of the laser diffraction system used in the cement labs. But this online system is much more stable and resistant to the intense vibrations occurring in a cement plant environment. Here's the question. Why is the online analyzer essential for cement manufacturing? And what would the online system benefit us? We can figure out from these figures. When grinding cement to smaller sizes, additional energy costs are incurred. So it is critical to measure and control the size of the final product, not to cost and definitely not to fine. Cement is milled to an appropriate fineness for the grade, but insurance over grinding usually takes place in order to ensure it is in specification. Why is this the case? Laboratory measurements for fineness are made in the lab typically every 2 hours. As there is no control of the grind within that 2-hour time frame, the cement may be too coarse and need to be reworked. Alternatively, there may be overgrinding, resulting higher energy cost and an excess of fines, which can also be detrimental to the final product, as the setting time is reduced and the cement cures too fast. The key advantage of an online fineness analysis is not just the capability to make the measurements every minute, but also to optimize the separator speed based on those online measurements. A benefit of that is to create a just in specification product all the time with a much tighter tolerance by closing the loop. We have already seen insurance over grinding is expensive but necessary if there's no feedback control for the process. However, what if there was no need to wait for the results from the lab control, and what would this benefit you? Firstly, all energy expended in insurance over grinding could be thus eliminated or minimized. An added advantage to this is the residence time of the cement in the mill is reduced, such that cement throughput could be increased by 5 to 7%, which would mean it could satisfy increased demand by the actual capacity provided. And this could result in a system payback time of less than 3 months. Another advantage is a decreased response time when changing the cement quality from type 32.5 to 52.5, for example, thus reducing silo contamination caused by changing over from one cement type to the other. In addition, a lower standard deviation in cement finance leads to a more stable product in terms of the short-term and long-term compressive strength. How do the online results compare to the laboratory system and other historical techniques? We have done tests. Due to the different optical systems used by the online and laboratory instruments, there is a slight difference in the measurement results. We should understand the good consistency of results obtained by both different types of instrument. So a good correlation between results can be achieved, but the absolute values are not always exactly equal. It can be seen from the figures. As the compressive strength of cement increases, the average particle size, which is D50, obtained gradually decreases, and the content of 3 to 32 micron percentage, which has the most important contribution to the 28-day strength of cement, increases slowly. Therefore, the measurement results produce a good correlation. In addition, tests have been made comparing the online system with wet sieve analysis. It is widely known that one of the laser diffraction advantages is to measure all orientations of the particle, so all 3 dimensions are taken into account. Sieves, however, only report the second largest dimension, and hence undersize irregularly shaped particles through ignoring the longest particle dimension. In situations like this, we have to accept there will be an undersized shift in the sieve results. They are not wrong, but they can be a little different depending on their aspect ratio of the particles. The important thing, however, is to make sure the sieve results check the online process results. And as can be seen, when tests were made comparing the online results with those measured by sieves, they checked with great success. If there was an increase in the percentage of particles larger than 45 microns on the online analyzer, then there were also a proportional increase on the sieves and vice versa. Besides, online analysis checks the changes in classified speed in real time, and with that control, they can really optimize the online classification process to provide real cement control management. Next, I would like to introduce 2 practical application cases of online systems in the cement industry. The first is Lafarge. Lafarge is a world leader in cement and concrete sectors. Since 2018, the online laser system has been installed on the cement production line of Lafarge and started real-time particle size monitoring. Here's a short story. One day, technicians of Lafarge found in the control room that the particle size test system showed a significant increase in cement particle size from 10 p.m. to 11 p.m. At the same time, the temperature control curve of its overall control room showed there were drops and fluctuations around 20 to 40. After the technicians conducted investigation, they confirmed that the mill speed was reduced at that time. So the increase of the particle size measured by the online monitoring system coincides with the decrease in the mill speed. By the way, during more than 5 months of use, Lafarge has carried out only 2 maintenance of the instrument, which was to clean the measuring area. So the maintenance cycle and instrument reliability are far beyond user expectations. Another application case is South Cement Company, which is the cement industry leader in China. South Cement uses a 3-shift system for work. After running the online particle size system, the number of people in each shift is reduced from 4 to 3. 2 sets of particle size results per minute are transmitted to the central control room in real time, and the feeding configuration is adjusted in time based on feedback. Compared with the original method, the monitoring efficiency is increased by more than 10 times. Last, apart from the particle size of cement, at the end of this talk, I would like to mention the shape importance of cement particles. We have already seen a cement particle size is now considered as critical for the determination for the quality of cement. Final particle sizes have a greater surface area affecting the cement's compressive strength and setting rate. However, the cement particle shape has also an influence. For example, if both populations have nominally the same size, spherical particles will have a lower surface area than cement that is irregular in shape. The required amount of water in a cement mix will reduce for spherical cement and increase as the particles become more irregular in shape. Cement particles are non-spherical, so are the additives such as gypsum. Gypsum is blended with the brine clinker to control the cement hydration rate such that its setting time is appropriate for the application. The shape of clinkers and additives will directly affect the product performance. After the particle morphology is improved, cement particles will be more densely packed and the setting time is prolonged. The fluidity of the cement mortar increases with the circularity. In the cement hydration process, shape of particles can cause detrimental effect as well. These are electron scanning images of calcium hydroxide and etchinite. The unusual shapes are indicative of the possibility of future problems caused self-realization. Now, a new generation of particle size analyzer is able to measure both the size and shape of cement, which will open up new research areas on not just optimal size, but also optimal shape. How does it work? The particles to be measured are pumped through the double measuring cell system in a solvent. In the first sample cell, short-wave laser, which is 532 nanometers, hit the particles, and is scattered depending the particle size distribution. In the second sample cell, the particles are continuously photographed, evaluated, and statistically classified by the image analysis system, consisting of 2 high-speed CCD cameras and high-precision telecentric lenses at a rate of up to 10,000 particles per minute in real time. After the test is done, the particle graphs will be displayed, reporting both the shape and size of cement particles. Finally, I want to make a summary about this talk. For cement industry, there is a great need for laboratory-based laser PSA to provide quality control on whether the current cement production is fit for purpose and whether to ship, blend, or rework the cement. It can effectively optimize cement production process and to improve the product quality, reduce energy consumption, and reduce production cost. There's an even better need to install a ruggedized online laser system, fully automated and based on the same principles, but with no need for human input. It can measure the cement fineness, providing key parameters in real time, and it can compare these current values to the optimal values saved in the computer placed in the cement control room. In a word, there should be a particle size analyzer in the lab for quality control and an online cement analyzer sending a control output signal to the separator in real time. Last, a new generation of particle size analyzer with its unique design is now able to provide not just optimal size, but also optimal shape of cement, allowing a shape analysis with more than 20 shape parameters. This is all I want to present, and if you are looking for more technical and application notes or webinars, please visit Bettersize website or contact me by email. Thank you for your watching.